Hello and welcome to this episode of the Kielder Observatory podcast. I'm Ian Brannan. Great to be back with you once again. Now, in this episode, we're trying to unravel one of the most complex topics of the universe, and that is of dark matter. We have an expert who knows all about it. Professor Richard Massey is an astrophysicist, and he's also one of the Royal Society Research Fellows in the Institute for Computational Cosmology at Durham University.
Whenever there isn't any stars or galaxies, there isn't any dark matter either. And there are these huge, vast, empty voids. And I kind of find those the most fascinating but sort of terrifying bits, where you stare out into the void. And there's these huge regions of the universe where there's absolutely nothing. It's completely empty.
It's all around us, but we can't see it. The subject of dark matter, explained with Professor Richard Massey shortly. Also in this episode, I'm joined by Maura Shapiro, who's one of the science communicators at Kielder Observatory, to also chat with Professor Massey about dark matter. But first of all, I join Maura at Kielder Observatory under a clear sky to have a look at what we can expect in the night sky at this time of year as we move from winter in towards spring. What can we see in our gardens, with our binoculars, with our telescopes, across the UK and further afield?
Right, so as you mentioned, we're under a glorious sky, and one thing we look for as kind of, as you said, winter changes to the spring sky is this gorgeous constellation Leo that we are facing actually right now, the Lion. You might notice it from its kind of very distinctive sickle asterism. So Leo, we say, kind of dominates the springtime sky. And around Leo is actually great for hunting down galaxies. So we say springtime is kind of galaxy season because some of the most rewarding stargazing you can do is looking for galaxies because they're hard to find. You can't see them with your naked eye, with the exception of Andromeda. And so you'll need binoculars or even telescopes to find these galaxies. We also have Jupiter shining very bright above us right now, but technically we just missed the so-called planetary parade. As astronomers, we kind of like to tamp down on excitement about things like that, just because planets are gorgeous and we love looking at them. But this planetary parade was pretty difficult to catch because a lot of the planets would have been very low on the horizon as the sun was setting. Other things to look out for in the next month or so. In April, we actually have 2 meteor showers, the first of which are the Lyrids, which is a great one to look out for, and they appear to originate from the constellation Lyra. So to catch that one, you'll want to wait until kind of the wee hours of the morning and face Lyra. You'll know the Lyra constellation from its brightest star, Vega.
That's always one of the first to see as well when the stars come out, isn't it, on a night as well? So that's kind of makes it easier for you to look for.
Yeah, and when you wait until kind of the morning hours, it will be at its highest point in the sky, so the best time to catch it. Other than that, in space news, following up on last podcast, the Artemis mission has been delayed. So we are hoping for a launch in early April, and then other changes have been made to the Artemis mission. So Artemis 3 will no longer land people on the moon. It will test out kind of the docking capabilities of the lunar lander. And then Artemis 4 will be the one where people land on the surface of the moon. But we're still looking forward to Artemis 2, getting people out to the farthest reaches of space, and kind of breaking ground in that way.
And is that in some way some response to the issues with Boeing? Of course, they were involved with the capsule, weren't they? And I think the findings have come out from that in the past few weeks, and actually it's been found that it was actually probably a worse scenario than perhaps they were letting on at the time, that it could have gone horrendously wrong. Thankfully it didn't, but there were obviously extra question marks maybe around that too.
Yeah, potentially. And I guess hindsight is 20/20, but it makes sense that they'd want to test out, how to dock the lander ahead of really needing it, because you never want to be doing something for the first time
on the moon.
On the moon, yeah. I forgot what we were talking about for a second. So kind of as more details come out, we'll learn more. But we are still looking forward to seeing what comes next for the Artemis missions.
Well, we're looking into into the night sky right now, and this is a stunningly clear night, I think, isn't it? And the evenings have been fairly few and far between, haven't they, so far this year?
Yes, I think there's been about 5, maybe, totally clear nights so far in 2026. So I'm kind of mesmerized looking at Orion. But next to Orion, we have the constellation Canis Major, which is very distinctive for the star that marks Canis Major, which means big dog. The big dog's collar, which is Sirius, which is sparkling quite a bit. And that's because Sirius is very bright and it's very low on the horizon, which means that the light coming from space, from Sirius to us, has to fight through a lot more atmosphere. And that's what's making Sirius sparkle so much. So sometimes people think it's like a plane or even a UFO, this really mysterious, bright, twinkling thing in the sky. But it is Sirius, the brightest star in our northern hemisphere.
I've heard it referred to as a disco star before as well.
Yeah, no, and
twinkling.
When you look at it through a telescope, you'll definitely appreciate why we call it that, because it literally changes color like a disco ball. So it's one of our favorite things, I think, here to get a telescope on, because it's so groovy.
But what about the stuff in space that we can't see, and that's dark matter? Well, we've got somebody who is going to tell us more about that right now. Professor Richard Massey is joining us this evening. He's actually joining in everything else that's happening at the observatory, and he's taken in some of the knowledge himself. But I'm sure he'll be imparting his own knowledge as well throughout the course of the evening. But we spoke to him earlier on the subject of dark matter, among many other things, and here he is.
I'm afraid we're not going to get to see any tonight because
dreams ruined.
Sorry, yeah, I know. Even with these beautiful clear skies that we've got here, I'm super excited to come up to Kielder. By the way, this is I've looked forward to coming here for a long time. We're not going to see any dark matter because, unfortunately, it's invisible, and that makes it kind of tricky to study, to know about, and to understand. And to be honest, we don't know a lot about it, but we know that there's a lot of it out there. In fact, it's kind of important to know about because it's the most common stuff in the universe. Everything that we're made out of, which is sort of normal atoms, carbon and hydrogen and water and things like that. Everything that we're made out of is a tiny fraction of what's out there in the universe. There's all this extra stuff out there. There's for all of the material in that. Everything that you can see, everything that you can touch, everything that we are, everything that you can see, even the stars that we can see, even the air around us. There's about 5 times as much material out there in the form of this invisible and still fairly unknown dark matter. Now,
you've attempted to map some of what we know, what is available, and you have focused on what is a relatively small area of the night sky, but nonetheless, you've just tell us about your findings from that.
Well, I mean, we want to know about this dark matter because it turns out that it's really important. We can't see it, but there's plenty of things that we can't see. I mean, for example, we can sort of look out across out of the dome. We can see sort of trees maybe swaying very slightly in the distance because there's wind blowing them. You can't see the wind, but you know that it's there because of the way that it moves and affects things that we can see. Now, dark matter is kind of similar. It's invisible. We can't see it directly, but there's a lot of it and it's heavy, so it has gravity and it pulls things around it. It sort of changes the orbits of stars around the galaxy. It changes it pulls the whole universe together. In fact, there's that much of it. So it affects things that we can see. It affects us, and has even changed the sort of whole evolution of the universe. That there's that much of it. So we want to know where it is, and crucially, what it is. We kind of want to know what it is because it's the most common stuff in the universe. To be honest, it's a bit embarrassing, really, that out of 1,000 years of science, we've understood a sixth of the material content of the universe. We know nothing about the rest. So we want to understand what it is, and the first thing that you do if you want to understand a new field, if you sort of encounter a new frontier, is make a map. You're going out into the Wild West, figuring out what is out there, what is what is the landscape? Well, first you sort of draw the landscape and see where are the points of interest. So that's what we've done with the James Webb Space Telescope. We've tried to make a map of the dark matter. Now, how do you do that if it's invisible? Well, it affects it affects things moving around it. It turns out it even affects rays of light moving past it. And we all think that rays of light travel in straight lines, right? That's something that we know since we're children. Light travels in straight lines. Completely wrong. Light travels in what it thinks are straight lines, but if it's moving past something very, very heavy, very massive, then even light rays get deflected very slightly. You can see that actually during a solar eclipse. The stars, if they sort of pass right next to the sun, if the light from the stars passes right next to the sun, when the sun is blotted out, so you can see the stars, then they're in slightly the wrong places because their light has been pulled very slightly by the sun on its way past them. Light does a similar thing when it passes near dark matter, and we can tell then from the sort of the bent rays of light that there must be something in front of it. Now, the way that we do that is we sort of take the James Webb Space Telescope and we look at galaxies. We look at very distant galaxies a long way away from us. And we might see one of them that looks a bit like the Milky Way. That's a normal shape. Fine, great. We might see one that's a big fuzzy blob. That's kind of normal as well. Then we see one that's this weird, distorted, curvy shape. And hang on, there's something weird about that. That's not the shape that galaxies are. And it's because there's a big lump of something massive in front of it that the light from it has to pass through to get to us, and it sort of distorts the shape of the galaxies. It could move the apparent position of individual stars. When you're looking at a whole galaxy, it would sort of distort it into this sort of characteristic curvy patterns, something that's really unusual that we know galaxies don't look like. And because we see this sort of distortion in the shape of a very distant galaxy, we know that there's some dark matter between it and us.
So if we've created, if you've created this map of dark matter, what are you hoping to learn from finding the location of it?
Well, the first thing that we do is find out where the dark matter is. And then the big question after that is going to be, well, what is it? So we find out where it is. And actually, it's fascinating what we find. So what we find is that wherever there's big concentrations of ordinary matter, there is loads of dark matter as well. So around... So we live in a place where there's lots of matter. We're in the middle of the Milky Way. Around galaxies like the Milky Way, there's tons and tons of dark matter just swirling around. In fact, dark matter is whizzing through us as we speak. It doesn't have anything to do with us. It just passes straight through. It doesn't cause any harm. But there's lots of it there, and it's pulling the whole Milky Way together. The Milky Way is a big disk of stars. It's sort of spinning round and round. It's turning really fast. And by rights, it's spinning so fast that there isn't enough gravity in amongst those stars to hold it together. By rights, it should have spun itself apart and flung all those stars out into the cosmos. Because the Milky Way has dark matter in it as well, its extra gravity holds the Milky Way together, holds all the stars in one place and lets it spin as fast. There's dark matter all around us here on Earth. I don't know if it's scary. I don't know if it's terrifying. It shouldn't be. But there's dark matter all around us. But we find that there's dark matter wherever there is ordinary material. And on the sort of biggest scales of the universe, we see that there are lumps of galaxies like the Milky Way. They don't live alone. They live in groups and clusters of maybe thousands of galaxies all hanging out together. And they're surrounded by enormous clumps of dark matter. We sort of learn from that dark matter and ordinary matter are attracted to each other through gravity. That's how dark matter sort of shapes the universe around it. It's attracted to ordinary material through gravity. But then sort of going away from those big concentrations of ordinary galaxies and dark matter, we see these sort of strings and filaments of a few galaxies dotted along, and then big strings of dark matter all around them. Wherever there's ordinary matter, there is dark matter, and wherever there's dark matter, we find there's ordinary matter as well. They come together. They come in a pair. in our map, another kind of cool thing that we see is that wherever there isn't any matter, wherever there isn't any stars or galaxies, there isn't any dark matter either. And there are these huge, vast, empty voids. And I kind of find those the most fascinating but sort of terrifying bits, where you stare out into the void, and there's these huge regions of the universe where there's absolutely nothing. It's completely empty. So that's the kind of spider web that we sort of see, a sort of a crisscrossing network of strings of dark matter with nothing in between them.
This is the cosmic web.
Yeah.
People talk about.
Yeah, it's the cosmic web. And it's lit up along, it's created of dark matter, but then it's sort of lit up with galaxies sort of as little dots. It's a bit like sort of if you fly over a country, then you can sort of see little, you see sort of concentrations of lights in cities, and then sort of strings of roads coming out from those, and you can see them all sort of lit up. The sky is pretty much the same as looking down from an airplane.
I love that illusion, because we often show people, our guests, images of countries from above to illustrate what it actually looks like to be in a dark sky park where we are here. So we show them what London looks like from above, just completely illuminated by street lights, and Europe with these population centers. So that's, I think, a very prescient way for many of the guests who've seen those images to imagine how dark matter kind of shapes our universe. When you say it impacts the evolution of the universe, is it through this galaxy clustering to dark matter?
Yeah. I mean, just sticking with that map for a bit, I think the sort of exciting patches of the universe, or terrifying patches of the universe, are the big empty voids where there's no matter. Well, I guess Kielder is the equivalent of that.
The void.
And then looking down, it's the best bit in the middle, away from anywhere. How does sort of dark matter affect the universe? Well, it keeps our galaxy together, but it's affected the universe in sort of even bigger ways, right back to the Big Bang. So just after the Big Bang went off, the material in the universe was sort of spread out into this big, bubbling, primordial soup, but it was fairly evenly spread out. And if the universe had stayed in that sort of mix where everything was uniformly spread out, then there'd be sort of atoms over here and atoms over there, but not enough of them in any one patch to sort of have enough concentration, enough density to end up creating planets and people. Fortunately for us, the primordial soup coming out of the Big Bang contained a bit of dark matter, and dark matter, in its sort of arrogant way that it passes straight through us and doesn't care about us, it didn't really care about this primordial soup either. It sort of separated out quite early from the primordial soup and started to become a bit lumpy. So there was a bit more dark matter in some bits of the soup than others. And because it has gravity, the dense bits of the universe where there's lots of dark matter sort of pulled in more dark matter, and that pulled in more dark matter, and more dark matter, and then that pulled in all the ordinary material, and it created, in fact, this cosmic web. It ended the smooth soup and smooth sort of well-mixed soup, and it separated up into these empty voids, and fortunately for us, the kind of regions where there's lots and lots of material in one place that could eventually form a galaxy and spark stars into being and form planets and people around it. So we owe our whole existence to the dark matter that started things.
So, as you said, we don't really know what it is. All we know is that it's invisible to us. It doesn't care about us. But there are a couple different theories as to what dark matter is. Do you want to talk about maybe a couple of the theories, and if you have any inclination towards one?
There are lots of theories about what dark matter might be. I mean, this partly comes from if you get a particle physicist in a room and ask them to invent a theory of what a new particle might be, then, well, every particle physicist you get in a room will come up with an entirely new theory. There's a whole zoo of ideas that there might be. But, I mean, there are some ideas. One of my particular... I mean, we can't have a favourite as such. I have no idea which bit of dark matter it's going to be. But then the act of science comes to it's sort of a question of looking under the lampposts. So if you're walking home, if you've walking home at night, you've been to the pub, you're on your way home, and you realise, oh, hang on, I've dropped my keys. I'm not going to be able to get in. I've got to, figure out where my keys are. They could be anywhere on the way home. Where do you look? Well, you walk back along the road and you look under all the lampposts that you can see where it's lit up, and you might be able to find your keys. It's not because it's particularly any more likely that your keys are there, but it's somewhere that you can at least test. And hopefully, as you walk back along the road, one of the lampposts that you look under, you've got your keys and you can get back into your house. We're doing the same sort of thing as we walk through the zoo of what dark matter might be. That there are certain tests that we can do. There aren't many because it's invisible and hard to see. So we can't test every possible theory yet, but we can at least look under some lampposts. We can test some things. And one of the things that I'm trying to look at is whether dark matter particles occasionally bump off each other or bump into each other. So if you want to know what something is made out of, the kind of thing that we do ever since the Stone Age, really, is to throw a couple of lumps of it together and see what bits fly off, whether it be a couple of lumps of rock or whether that be under Geneva at the CERN particle accelerator, where you'd throw a couple of protons at each other and see what their protons are made out of by seeing what bits come off. I'm trying to look at what happens if you throw lumps of dark matter at each other, and you can maybe tell from that what it's made out of. You can tell from that what forces dark matter responds to. And that's basically the same question. We are what we sort of do in the world. The dark matter map has been, for me, like the lamppost in the street. It's been useful for sort of showing us where to look at dark matter more. What interesting parts of the universe might there be that could tell us more about dark matter? It's important to find the right patch of universe, because the catch about astronomy is that we just don't have labs. We can't, we can't do experiments and play around with things. We couldn't anyway if it's dark matter. You can't pick up a lump of dark matter to throw it at another one. Even if you have a particle accelerator, you just can't interact with dark matter. It passes straight through. But fortunately for us, in the map, we've found regions of the universe where nature has done the experiment for us that's exactly the right experiment, exactly what we want to do. There happen to be patches of, occasionally a couple of big lumps of dark matter happen to be right next to each other, and because they're pulled together by gravity, pulled towards each other, they smash into each other at high speed. And by looking at these big concentrations of dark matter as they smash into each other and seeing sort of basically where the bits fly off, we can hopefully try to work out what it is. And if my sort of favourite theory is it turns out to be correct, although dark matter particles whiz through us and don't bounce off us, occasionally they might bounce off other dark matter particles, and that would mean that when two big lumps of dark matter pass through each other, they will slow down slightly, like a very sort of slow motion car crash, and sort of stop closer to the point of impact than they otherwise would.
And what would that mean?
That would mean it would be incredibly exciting, actually, because we know so little about dark matter. Well, we know lots of things that dark matter doesn't do. We know that it doesn't emit light, it doesn't absorb light, so we can't even see it in silhouette. It doesn't interact with us, it passes straight through us. We've had experiments at the bottom of mines trying to wait for occasionally just one dark matter particle bouncing off us. Nobody's seen anything. We know all these things that dark matter doesn't do. And ideally what we would like to find is something that dark matter does do. And if we could catch it in the act of slowing down, of bumping into other dark matter, that would be the first positive thing that we'd know that dark matter actually does. And it would be the first step to finding what it is.
Just looking ahead to the next couple years, decade, what do you think we'll start to slowly learn about dark matter? Where do you think the field is going?
The next few years are really exciting for studies of dark matter in the dark universe, because there are several telescopes which have for the first time been sort of custom built to try and study it. And this started with the Euclid Space Telescope, which is a European Space Agency mission, which launched in 2023. And that the first data that's been actually, it took 6 months to get it. It's a long way from Earth. And it's so far away from Earth, it's 1 million miles away from Earth, so a bit like Kielder again, in the sort of dark, empty reaches of space where it's nice and quiet, where it's away from any bright lights, and it gets a great view of the night sky. It's gone to the Lagrange point too, the other side of the Earth from the Sun. And in its quiet environment, it's been slowly taking photos of the night sky. And unlike something like the Hubble Space Telescope or the James Webb Space Telescope, which have sort of basically a zoom lens that they can take a really high resolution image of a very small patch of the sky, Euclid has a big wide angle lens, so it can actually take this still high resolution, but an image of a large patch of the sky, and it's been gradually taking photo after photo after photo, almost in panorama mode, where it can piece together, eventually over the next six years, it's going to piece together an image of the whole sky at super high space resolution. But in September or October, it's going to release the first data from that is going to be made public, which is an image of the first sort of third of the sky or something. And we're not just looking for all the stars and galaxies and stuff that it sees, but it's been designed in a way that we can look at the shapes of very distant galaxies and learn from all of those where the dark matter is in front of them, and then create a map of dark matter, which is not just one or a small patch of sky, which is what we've been able to achieve so far, but we're gradually building up a map of dark matter around the whole universe, all around us. Eventually, by the end of the 6 years of the Euclid mission, it's going to be a map that's all the way around us, a huge map of dark matter everywhere in the universe, with a tiny little dot at the centre saying "you are here." But that's going to be the starting point to then do even more studies and look at more of these collisions, or look at more of the interesting galaxies and places where dark matter is potentially doing something interesting to try and catch it in the act of doing something.
What makes Euclid specially designed to be hunting down this dark matter?
So Euclid, to see dark matter, you have to study the shapes of galaxies, which are a very, very long way away. You have to look at the shape of a galaxy behind any dark matter that you're interested in. So these galaxies necessarily are very small and very faint. And you have to measure their shapes incredibly accurately, it turns out, because we're looking for very small distortions to the shape of a galaxy. It might change its shape. It might it's sort of the length to the width ratio of the galaxy might change by 1%. It might be really small, but nonetheless, that would tell us that this where the dark matter is in front of it. And so Euclid we designed it in a way that it will be in nice dark skies, but it's not just dark actually away from the Earth. It's also its temperature is incredibly stable. There's a problem with the Hubble Space Telescope that every time it orbits the Earth, it's close enough to the Earth that it keeps passing in and out of the shadow of the Earth. And when it goes into the shadow, it cools down very, very slightly. And then when it comes back into the sunshine, it warms up again, but it expands a little bit. And that's constantly putting the telescope very slightly in and out of focus, because the whole telescope stretches and expands only by a couple of microns, a couple of millionths of a meter. But nonetheless, it's enough to blur out blur the images in a way that isn't quite easy to predict. Euclid is 1 million miles away from Earth, and so it never passes into the Earth's shadow. And in fact, it always keeps the same side towards the sun, so that it's always thermally really stable. This telescope is just sort of permanently well controlled, so we get repeatable images all the time. And because of that, we can measure the shapes of galaxies. It's not that a galaxy looks weird because it's slightly out of focus at the moment. It's because this galaxy really does look like a weird shape. And because we can then map it at very high resolution from space, you get this crystal clear view of the sky. You can look at the shapes of galaxies, look at galaxies a very long way away and all over the sky because of its wide angle lens. So we get this huge map.
Well, this all seems incredibly exciting. I think you've made a really excellent case for why it's important to study dark matter. It's the reason we exist. It's the reason why galaxies are the way that they are. But sometimes we come across people who think, why are we investing so much money in space when there's so many things still to understand about people? There's so many problems on Earth. And one of the main arguments we have is kind of the spin-off that we get from studying space, the spin-off technologies, and you're doing a little bit of work around using some spin-off technology for cancer. So would you like to talk a little bit about that?
Yeah. I mean, first, there's the intrinsic value of doing science in itself. I think you're right. It's a tough call because there are lots of problems that are perhaps more urgent, well, definitely more urgent than figuring out what the universe is made out of. But I would still argue that the intrinsic value of science itself, about trying to explore the universe, trying to figure out why we're here and what's going to happen next, and make maps of what is out there, I think that's what's driven humankind for our entire evolution. And I think it is important to still keep doing that, at least at some level, purely for the sake of doing it and exploring and satisfying that human drive to know why are we here. But you're right. It has sort of historically been an issue that the benefits that astronomy and astrophysics bring tend to come 100 years later. And while it's great to know what electrons are, and the person who discovered electrons might not have thought, or didn't think that they were going to be very useful. Turns out they are. We don't think that dark matter is going to be very useful, but maybe 100 years from now it is going to be useful. But this is all sort of a long way into the future. So I've been very lucky recently to be able to get involved in a way of sort of paying back some of the time and investment that people and the taxpayers' money has gone into funding some of the astronomy research, and Euclid in particular. And that's that it turns out that looking at lots of galaxy shapes and sort of categorizing these galaxies and knowing, okay, this one's got spiral arms, and this one's an old thing, this one's doing well, that one's just recently had a collision, a merger with something, and so sort of wanting to classify their shapes for whatever reason, but knowing that there's some underlying physics behind it all, the physics of how stars form and how gravity pulls things together creates those different shapes. Turns out that that's very analogous to some of the problems facing healthcare and facing sort of cancer diagnoses, that you have in medical data lots and lots of data about all sorts of different people. And you might have a cancer patient come along, and they've got a particular genetic sequence, or their tumour has a particular genetic sequence. And someone else comes along, and they've got a different genetic sequence. They're maybe suffering from a similar type of cancer, but there are rules, there are sort of biological laws that govern how those tumours will evolve. And we want to try and find an underlying theory, or in fact, to be more practical, what we want to find is what medicine to prescribe to those people. And some of the statistical techniques that we've developed to classify the shapes of galaxies, we've been able to turn those round and say, well, look, if we can figure out that people who've had a tumour with this sort of history of symptoms and this genetic sequencing in the past have responded well to this this chemotherapy, but not that one, well, then maybe someone else who comes along in the future, we can spot the statistical pattern that person might respond well to this particular treatment as well. This would be terrific. I mean, obviously, to have individualized, personalized medical care, you would get the right treatment. It's great because at the moment, the doctors just don't necessarily know what treatment to prescribe to people, and so typically that a patient might be given 2 or 3 different therapies. Well, these are all really horrible things to go through. They're toxic, and they're just nasty things to go through. They're also expensive. So for the NHS, it costs a huge amount of money. But if we could say that, look, based on comparison to previous patients, and based on the response of this particular tumour's genetic code in a lab, in a test tube, then the right treatment, or the most effective treatment would be this. Go with just that one, and crucially, it's important to have that sort of evidence, or the sort of the traceability of where does the evidence come from. We've been able to bring in some of the statistical techniques that we developed to try and to create a back end to some software, which hopefully is being rolled out into the first oncologists' treatment centres next year.
That is really exciting and really cool application of statistical methods for physics branching out. So I'm kind of curious how you found this interdisciplinary overlap. How did this come about?
It was a bit funny, actually, that because I don't often talk to oncologists. It was a postdoc that I've been working with, James Nightingale, who's also at the University of Durham, he happened to be in London. He happened to be at a WeWork office, one of those shared office spaces where you can rent a desk for a day to just have somewhere to sit down and do your work while you're away from home. And he was sat down working on a problem of the statistics of these galaxies, and was thinking through this thing to himself and the person next to him was having a little conversation, was working through another statistics problem, and they sort of crossed eyes and sort of realised that they were talking basically about the same thing. And by sheer coincidence, these two people had been sat down. Well, James was a cosmologist, and the guy next to him, Matthew, was working for a startup company, Conquer, who are developing all these treatments for cancer, and they had, it turns out, exactly the same issue on that exact same day, and they happened to be sat at the desks next to each other at WeWork. So WeWork has been a terrible failure. If you've bought shares in WeWork, disaster. But they've done some very good jobs.
There's also a punchline in there: a physicist and an oncologist walk into a WeWork. It's a setup for something.
Yeah, it's got to be. But, hopefully some good things have come out of it.
You're looking at telescopes yourself to maybe help look for life in other worlds as well, which is something that people are always fascinated with that prospect. Obviously, you're talking about dark matter, but tell us about your thoughts and your studies in that department.
Yeah, we're designing a telescope at the moment with NASA that's hopefully going to launch about 2040. So it's a long time in the future, but it's going to go into space. It's going to be about 8 meters across. 16 inch. It's going to be huge. It's going to be 8 meters across, and it's going to be designed specifically to look for life, for habitable planets, and maybe even inhabited. It's being designed to, for example, to have a coronagraph. That's where you can look at a star and block out the light from that star, and see the very, very faint light from a planet right next to it. So we know that there are lots of planets around. Most of the stars in the Milky Way have planets. That's been the big discovery of the past 20 years. But they're very faint, and they're right next to something really bright, another sun. So they're very difficult to see. We only know about them indirectly. It's a bit like dark matter, really. We only know about them mostly because their gravity pulls the star backwards and forwards a little bit. The gravity from the star pulls the planet around and around and around, but the gravity from the planet makes the star wobble very, very slightly. So we know that the star's there because we can see the planet moving. But for most of these stars, most of these planets, we haven't been able to image them directly yet. This telescope is going to be is designed precisely to do that. It'll see something 10 billion times fainter than a star right next to it, even if that's the light from a very small Earth-like planet.
And of course, quite a bit of James Webb has its origins in the northeast, through the imaging and through work done by academics at Durham University as well. So is this to complement James Webb? Will this be the success to James Webb in the long run? Where does it fit into the scheme of what's in there? Yeah,
so it's NASA has a whole sequence of great observatories planned. The next one's going to be the next one's going to be the Roman telescope, which is a bit like ESA's Euclid, but they're slightly behind the curve on that. ESA beat them. But the one after that is so there's been Hubble, James Webb, Roman, and the next one after that is going to be this Habitable Worlds Observatory. It's very it's similar in some ways. It has a similar sort of segmented mirror to James Webb, built up of lots of hexagons, which can all be moved individually to make sure that the mirror is perfect, unlike Hubble's was when it was first launched. But it's built out of these similar mirrors to James Webb. But while James Webb was infrared, and it looks at the long wavelengths, red wavelengths of light, the Habitable Worlds Observatory is going to look at ultraviolet, optical, actually, and slightly infrared as well. But crucially, it's going to look at these shorter wavelengths of light, the same that we see. And that's crucial because the signatures of life, like us, if they're similar around other planets, well, certainly the signatures of common elements that we're involved with, of oxygen and water and hydrogen, and those make impressions on our atmosphere. Sort of absorb light, the oxygen, the ozone, for example, or the water vapor in the upper atmosphere absorbs light at 120 nanometers. That's bluewood of what we can see. So you couldn't see that with the James Webb Space Telescope. You have to look for signs of life and habitability by looking at if that life and is anything like us and built out of the same elements as us. You have to look at different wavelengths.
And so what's your hunch then when you get if the telescope's in space and you can point it in one direction, where are you heading with it? Where do you think you'll find potentially where's the place where you, I don't know, feel most confident that would be a habitable world in that part of the universe?
Well, we've actually got the targets mapped out already. We know that there are lots of stars around lots of nearby planets, and it's easiest to see these things if they happen to be near to you. So we're going to look at the 100 nearest stars because they're near, you can study them better, and if there's an Earth-like planet going around them, then at the separation of the Earth from the Sun, then it would appear further away, so you can resolve it a bit better. And so we've got these maps of exactly which 100 or so stars that we want to look out for. Even my favourite is just the nearest star to Earth, that Proxima Centauri is itself host to certainly one planet which is even in the Goldilocks zone. So it's not too close to the Sun that it's so hot that water would evaporate and boil. It's not too far away that it's cold. There is a star. There is a planet. It's quite massive, but it's probably still made of rock. And it might even have liquid water on the surface. So that's clearly the first one to look at.
Relatively on our doorstep in space terms.
Well, relatively on our doorstep, yeah. But so we're quite excited at Durham that maybe we'll be able to build some of the bits to go on that. We've been invited by NASA to see if we can. Like you say, for the James Webb Space Telescope, we built bits of that plenty of bits of that were built in the UK. Some of it was assembled in this high-tech space park just outside Durham, and with Durham University. The camera then was assembled in Edinburgh, and that was shipped off to the US to be launched, and it's performing incredibly well. So it's just nice that in the UK we can actually contribute to these things and build some of the best, the sort of highest tech detectors and cameras that are available in the entire world, and they're being used in space telescopes by NASA.
And even in the northeast as well, there's quite a strong space scene in terms of research at the various universities. Durham, but also Newcastle have their own interests, and Northumbria are launching their new space department as well, aren't they? So between the academics across the whole of the northeast, really, there's a lot of space knowledge and a lot of research and development going on that's directly being used.
Yeah, we're trying to get the N7, the northeastern universities together to encourage precisely this. We've got various schemes set up to help the universities work together in promoting the fantastic engineering that's available in the northeast. Like I say, bits of the James Webb Space Telescope were built just outside Durham. And we're also crucially trying to get those universities and funding those universities to work with local industries to build some of the bits and to build some of the communications and the back in computing and all sorts of things that go with a big telescope or big space mission to bring all this industry to the opportunities available to the northeast.
Well, if you need an observatory to help out, of course, we're more than happy to be involved. Thanks for joining us, Richard, and making the journey up here. I hope you enjoy the rest of your trip while you're here too.
I'm super excited to be at Kielder. In fact, I'm super excited to be at any observatory at the moment. I used to work a lot at different telescopes, and it's really exciting. It sort of brings back it makes astronomy real and sort of literally down to earth. In recent years, I've been working with these space telescopes, which is great. It's all very cool and very high tech. But then you sit behind a computer looking at the images and telling it where to point. I love and I really miss being at a telescope and sort of being back in the in the real cycle of astronomy, of knowing exactly when the moon is and where the weather's coming from, or what directions the wind's coming from, and being able to just step outside and be really back with nature, which is the fun thing that got me into astronomy in the first place. And you lose if you go into space.
Well, the stars are starting to come out now above our heads.
Jupiter.
It is Jupiter.
You've heard it here first. This is better than the James Webb Space Telescope.
There you go. Who needs to go to space? Coming to Northumberland. It's far better. Richard, thanks for joining us, and we'll speak to you again soon. All the best for everything you're working on, and enjoy your trip here today.
Oh, thanks.
My thanks to Professor Richard Massey for joining us in this episode, and also to Maura Shapiro from Kielder Observatory. Now, if you'd like to come and join us at one of our events, either at the main site at Kielder or at the Twice Brewed Inn, which is also now offering your chance to get yourself stargazing, and come to one of our sessions at the Twice Brewed Inn, which is not far off the A69 up by Hadrian's Wall. So 2 separate locations now. Get yourself onto kielderobservatory.org and you'll be able to see everything that's available. And of course, there are some kids sessions also coming up as well as we get towards the various school holidays, Easter, there's various spring bank holidays and across the summer as well. So you can get online there and book well in advance right now. Thanks again, and of course keep up to date with everything happening in the night sky. kielderobservatory.org, the place to go, and follow us on social media.